Welcome to this lecture on sampling. We will discuss the application of Fourier transform in sampling. We will show the sampled Fourier transform to be periodic. We will discuss what is fast sampling, what is slow sampling. We will also discuss the minimum speed at which we should sample. We will discuss aliasing. Let the continuous time signal UA be sampled to produce UN. Recall that this is analog signal and this is discrete time signal. So U of n equals UA NTS. So this is the analog signal sampled at equal intervals of TS. The resulting discrete time signal is indicated as UN. This n is an integer, it goes from minus infinity to plus infinity. Recall the Fourier transform pair for the analog signal. This is the time domain signal, this is the Fourier transformed signal. We have already derived this earlier. Similarly, for the discrete time signal, it is this. What we will do is, we will substitute the expression for UA from here, that is the analog expression. For the discrete time, we will substitute from here and we will get a relation between the continuous time Fourier transform and discrete time Fourier transform. So let us substitute here. So I get this expression. So for example, UA of NTS comes from here. So UA of F. So wherever this small t is there, I will put NTS, all other things are identical to this. Similarly here, for UN, I substitute from here. Okay, I do not have to make any changes, I write it down directly. Okay, this is the expression we had in the previous slide. In the right hand side, I will write TS as 1 over Fs. Recall that this is the sampling period, Fs is the sampling frequency. So I get this. By LHS I mean the left hand side. I write that and I write the expression for F as capital F by capital Fs. Recall that this is how this small f is defined. And similarly here also, in the place of small f, I write capital F by capital Fs. Fs is the sampling frequency, and because I have df here, I have d of capital F by Fs. You will have to recall this expression 2 slides from now. So you may actually want to write this down in a piece of paper and then I am going to use this subsequently. Whereas the right hand side is given by this expression. So in the next slide, we will simplify the right hand side and then we will make that equal to the expression in red. Let us start with the right hand side here. I am going to split this into small integrals, k minus half to k plus half. The next one will go from k plus half to k plus 1 and a half, then k plus 1 and a half to k plus 2 and a half, and so on the positive side. Similarly on the negative side, that happens when I allow this k to go from minus infinity to plus infinity. So these two expressions are identical. Next what I will do is, I will write capital F as q plus k small fs. I will say that f is this and q being a dummy variable. So if f varies from k minus half fs to k plus half fs, it is easy to show that q will vary from minus fs by 2 to fs by 2. I would want you to verify that this is indeed correct. Now what I will do is, I will multiply these two. Here you have k times fs and then you have divided by fs. So when I multiply, it will be plus k. This will produce a multiple of, integer multiple of 2 pi. As a result, you will get this back because this expression is periodic. So you will get this back, and after that what I will do is I will replace this q by f, because notice that this q is a dummy variable, I can replace it by f. So it requires further simplifications. What I will do next is to exchange the integral and summation sign to get this expression. Of course, you have to make sure that it is possible to exchange these two, so we make that assumption. Recall the expression asked you to write down. It was marked in red 2 slides ago. This was the left hand side, this is the right hand side. Now we know that these two are equal. Notice that the integral limits are the same, this multiplying factor is the same. So we have this particular thing is equal to this u with a scaling factor 1 over fs. So I get that. When I equate the two, I see that 1 by fs times this is equal to what is inside the bracket. So let me write that here. So what I have on the left hand side has come from discrete time, what I have on the right hand side has come from analog or continuous time. When I cross multiply, this fs comes here. Now I expand this, so I get this expression fs into sum of infinite number of terms ua of f0, f0 plus fs, and so on and so forth. This is the value I will get if I substitute f equals f naught here. Okay. So it is easy here to see that this expression is periodic in fs. For example, if wherever f naught is there I add f naught plus fs, this whole thing gets shifted by 1 to the right. Similarly, I can subtract fs, it will shift to the left, but the expressions are all identical. So you can see that this expression is periodic in fs. Now we will see the two expressions, namely ua of f and u of f by fs. Recall that u of f by fs is obtained by summing this ua over infinite terms. See that, let us go back and see it again. This u is obtained by summing up this ua over infinite terms, which is what we have. And of course there is a scale factor of capital F, which you can see from here, because to get this u you have to multiply this analog by fs. So you have to multiply this analog by fs to get that. In other words, the shape is the same, but the height could be different depending on fs. Here the height is 1, here the height is fs. We have already said that this expression is periodic in fs. After every fs it will repeat itself. So as a result you see that the period is marked as here with this line, these two lines here. So you can see that this is minus fs by 2, this is fs by 2, the distance between these two is fs, and so until the next instant comes it will repeat itself. It is repeating itself, similarly it is repeating itself. So notice that u is a scaled version of this ua, the shape is not affected by sampling. You get the shape exactly here. Moreover, because of this, ua can be recovered from u. Supposing I look at this and I take out the middle portion, I will get this back. So while we are talking about recovery, we have to understand the sequence in which we carry out the calculations. This is the real time signal we have, but notice that we do not measure this. We measure only these points. We measure only at sampling instants. So given this, we only have the transform of this, which is this. and what we want to know is, can I recover this, even these points. So I measure these points, note down these points, take Fourier transform, I get this, take out the central portion, scale it down by Fs, so I get this. Now I take inverse Fourier transform, I get this. So in reality we start from here, we go like this, we come back here. So we say that UA can be recovered from U, or small u sub a can be recovered from small u n. So as I mentioned, what we have here, capital U for discrete time is periodic in F with a period Fs. From the same figure we can get the condition for the recovery of the sampled signal. Notice that we can recover this analog waveform from the discrete time waveform, because what you have in the middle is not distorted. It is not distorted because this Fs by 2 lies outside of B here. You can in fact see this here. Fs by 2 is greater than B. So we write, for the recovery of continuous time signal, Fs by 2 is greater than B. So this says that we should sample at least twice the bandwidth. So B is the bandwidth, beyond B we have taken the analog signal not to have any component in the Fourier transform domain. So in that case you fix Fs by 2 outside B, then you can recover the analog waveform exactly from the sampled waveform. What happens if you do not sample it fast enough? What happens if this Fs by 2 is smaller than B? So notice that B will come here, it is where this ends, so over here, whereas here we have taken Fs by 2 to be smaller than capital B. As a result, you can see that the waveform from the next period overlaps here, and when I add these two I get this waveform. I no longer have distortionless waveform in the middle. So if I were to take out the central portion, I will get only a distorted waveform, I will not get the original waveform. So this is the consequence of aliasing. The value of capital U at F naught is the analog expression, plus you get it from the next period. So overlapping value plus the value of the analog expression itself. So we cannot recover UA from AU, we cannot recover UA from U, as the high frequency components have changed here. What do we do if aliasing cannot be avoided? What if we get a signal, analog signal, that seems to have lot of frequency components for all frequencies, okay, so that you will always get aliasing no matter what sampling frequency you choose. What we have to remember is that no realistic system can have frequency components at all frequencies. They should have a finite bandwidth, however large it is. So one should get that idea from the domain knowledge. Somebody who is familiar with a particular domain will be able to say the maximum frequency that they will encounter in that domain is so much. So using that you can say that it should actually end here, everything beyond that is noise. So you filter this first and then go through the process that we described in the previous slide and you will get this. So filter out the highest frequency components. Every physical system has finite bandwidth. This brings us to the end of this presentation. Thanks for joining. Goodbye.